Okay, so right now we're kind of in a bit of a weird place because the concepts that we need to talk about kind of build off the idea of the shear moment diagram, but then we also, after that, need to talk about like what comes after shear moment diagrams. So what we're going to do is basically just have a little mini introduction to shear moment diagrams right now, and then we'll talk about them in length later. So the idea with shear moment diagrams is that if I have a beam right here, right, and I have some forces, some applied moments, whatever onto them, I can graph the internal shear force and the internal moment as a function of basically the length across the beam, right? So if you imagine right here, like I've got my section of my beam, bada boom, right here. So if you imagine for just for a second that AY is 0, then there would be no internal shear force in this section right here. But as soon as I encapsulate this P right here, in order to cancel with this P, there would need to be an internal shear force pointing in this direction, right? In the upward direction, which is counterclockwise, which means that our convention is that it's negative shear. And it turns out that it's the same thing for distributed loads, but it'll basically just go linearly downward as you accumulate more and more force. So when we graph this, basically what we're going to have is our AY is probably going to be upward because all of this is downward, right? So our AY will be upward. It'll give us a jump basically to some point right here. This would be our value of AY. Then we'd come over here, be constant, constant, constant until we hit P. Then it's going to decrease. And then we're going to get W, where it's going to decrease linearly like this. And then it's going to be constant until we reach this point right here for P. I guess I can just go and do some dashed lines so you can see what's related to what. This goes here. Then we're going to get another discontinuity. And that's going to be all the way to here until BY. In this case right here, it's going to go back up to 0. It always has to start and end at 0 because all of the forces in the y direction have to cancel out, right? And then we can also do the same thing for the internal moment. So basically, the internal moment's a little bit more difficult because each of these forces is going to contribute to it. But what we'll see later is that basically it's just going to be the area under the shear curve, right? So if this is constant, then it's going to be a straight line. So we'd have like a straight line like this, and then you notice that the slope decreases, and then we have a downward line, which would give us a parabola. So we would have basically something like this, and then we would have it going up again. Man, it's going up a lot. I should draw this a little bit lower to scale, and then it'll go up linearly, and then finally we get it going downwards. So I'm just going to do something like this, down to 0, and the moments again have to be at 0 right here, except for this M right here, which when we apply it, if you just think about it, is going to make it want to bend this way, right? If we're basically applying a moment in this direction, this side's going to get bent up, and this side's going to get bent down, which is going to be positive. So we technically need to add a positive jump right here, and then we keep going back down. These graphs got a little cluttered, but hopefully you understand what's going on conceptually. Now mathematically, without these jump discontinuities, so basically whenever we apply a load P at a single point, or a moment M, that's going to create a jump either upward or downward, right? But if we're just examining our beam with some distributed load W, then if we take a look at basically a slice of that, what we have on the left is our internal shear and moment, and then on the right is our shear and moment on the right, which I'm just going to call V plus delta V, and M plus delta M in this case. And then we have a distributed load up here, W. We have a W here, and then it might change here. And then we're saying that the area under this whole thing applied at the centroid, which we're going to call K times delta X. So our width right here is delta X. Some constant K multiple of delta X is going to give us the distance right here to the centroid. And then we're going to go ahead and say that W of X times delta X is the area under this distributed load, which is the equivalent applied force. Now, technically, this isn't true because this area under here could be something like this, right, which isn't the area of a square or a rectangle. But once we hit the limit as delta X approaches 0, this is what it's going to converge to, so we're just going to go ahead and not worry about it for now. So summing all the forces in the y direction, this has to equal 0, so this will be our shear force plus W of X times our delta X, and then we'll have a minus this shear right here, V plus delta V. So our V's will cancel out, right, and then I can add over my delta V, and I get that my delta V equals a W of X delta X. And now I'm going to go ahead and do the sum of the moments about point A right here, giving us fast equals 0. So for my shear force, it's going in the clockwise direction, which we're going to call negative. We'll call this direction positive for summing our moments. Maybe I'll put this over here just so it's a little bit easier. In the clockwise direction, which is negative in this case, we have a delta x times the shear force. We'll have a negative v delta x, and now we'll also have a negative k delta x times w of x delta x. So minus w of x delta x times our k delta x. All right, now we also have a minus m and a plus m plus delta m, so minus m plus delta m. Again, our m's are going to cancel right here. And if we go ahead and solve for our delta m, we get that's going to equal our v delta x plus w of x k delta x. And now for both of these, we can divide everything through by a delta x and take the limit as delta x approaches 0. So in this case, what we're going to get is that our dv dx just equals w of x. And then for this case right here, notice that when we divide through this first term, we're just going to get a v. And the second term is still going to have a delta x term. So when we take the limit as delta x goes to 0, this entire term is going to go away. So our dm dx equals just v, or I guess we could say v of x. Either way, it's just equal to the shear force. So now look at what we're saying. We're saying that the change of shear with respect to x is equal to this loading. And so our change in shear force, right? Let me use green. And so the change in shear force, delta v, is going to equal the integral of our w of x dx. And then we can also do the same thing here, right? The change in the internal moment equals the integral of our v dx. So coming back up here to the diagram, our w right here is basically negative and constant, which means that the area under that, which will give us our change in v, is just a linear term. And then for our moment, when we had a linear term, the area under that is a quadratic, and the area under the constants are linear. So if you understand that these applied loads create jump discontinuities, and that these diagrams are related by the integral and the derivative, then you can map out what the internal shear and moment is going to be at each location. And that can allow you to do things like solve for the maximum shear or moment across the entire beam. So now we're going to talk about bending. And this is what happens when you have an internal moment in your beam. So basically, if you look right here, we'd imagine that I have a moment like being applied like here and here. And that's going to cause the beam to kind of curve upwards in this U shape right here. Now the derivation here, we're going to also assume that there's no shear force, so V is 0, and no axial force. And then we're going to say that the approximation is close enough for most loadings, like the error is small enough that it's okay. So the idea here is that if we have a constant pure bending, so a constant m, then we're going to be bending in a circle basically, because as we move each increment along, there's going to be a constant amount of bending per length that we move across. So basically you have a constant radius of curvature, right? So we're going to call this radius rho. It's going to point from this point right here to this line right here. You see that this is NS, that stands for the neutral axis. So basically the neutral axis is the point where there's no compression or tension. Because if you imagine here, normally all of these, you can think of them as like fibers along our little thing right here. They're all at the same length, right? But then when I bend them, the ones on the bottom are going to get stretched out. So they're going to have a positive tensile normal stress. And then the ones on the top are going to get compressed. But right at the middle there, we're going to have the neutral axis. And we'll see that this occurs basically right on the centroid of the cross section. So again, just some notation right here. Rho is our radius of curvature. Then we have y pointing to some point that we're interested in. We'll call this whole length right here delta x. And then this point that we're interested in will have a length delta x prime, and then its radius will be rho minus y, right? All right. Now, if we go ahead and we look at the strain, we'll start with the strain and then we'll get into the stress. The strain is our delta over our original length, right? Which is going to be, you know, the limit. If we're looking at like a an infinitesimal slice, we'd have to take the limit as our delta x goes to 0. And then the numerator here will have a delta x prime minus our delta x, because our delta x is our original length, or our unchanged length, all over delta x. And then this is basically, I forgot to label it here, but this will be theta, right? As theta approaches 0, this length also approaches 0. So we can rewrite this as the limit as theta goes to 0. And then here we're going to say rho minus y times our delta theta. I think I use delta theta here instead, since we're looking at like a change in theta angle from here to here. And if you remember, radians are defined such that if I take my angle and I multiply by the radius, I get the length. So this is just the same thing as the arc length at this radius rho minus y, which is our delta x prime. And we'll have to subtract rho delta theta, and then we'll have to divide this all over by our delta x, which is just again rho delta theta. And now if we, well, let's see right here, we can cancel out a delta theta from each term, right? So these delta thetas go away. And then we also have rho minus y minus rho, so these rho's will cancel, and we'll just end up with a minus y over rho. This right here is the strain when we're looking at like a curvature or a bending, epsilon for strain. All right, but what about the stress? Well, for the stress, it's going to be a little bit more complicated. Basically, what we're going to have is, like I told you, we have compression on the top right here and tension on the bottom. So another way I can write this is basically we have compression right here if we're looking at a side view, right? This would be our cross-section. This is also the cross-section right here. So we've got our compression right here and our tension down here, and it's linear because basically we have this constant bending moment, right? And as we move further away, right, R cross F gives us our torque or our moment. So it's going to be linear like this. And if we look at the cross-section, we're interested in some slice dA. We're going to say that's some height y above this neutral axis right here. Okay, so we're going to start by, what's a good spot? We'll just do this. We're going to start by summing all the forces in the x direction, right? So because we're looking at our dAs right here, we're going to basically be integrating our differential forces, which is going to be an integral over the whole cross-sectional area of our sigma x dA. All of that has to equal 0 because we're in static equilibrium. So you have 0, and then from our equation, if you remember up here, we calculated the strain. So this right here is this, and then if you remember, we also have the modulus of elasticity, which is basically the ratio of our stress to strain. We talked about this earlier. Basically, it's the slope of that stress strain diagram. So if I multiply E times epsilon, I'll actually get my stress. So I can say that this is equal to the integral of, and then I'll have a negative y over rho. So I'll have a negative integral, and then I'll have E times y over rho, and then all of this is dA, which means that either E equals 0, which can't be true for a solid because it's basically like a constant. If E was 0, then we would have basically a stress strain diagram would be infinite, which means that it would basically just instantly break, which isn't how a material works, right? All the materials that we're going to look at anyway. Or the other things that could be happening if this is equal to 0 is that our rho is approaching infinity, which would mean that the radius of curvature approaches infinity, which would mean that we would have no bending. Or the last case is that this y dA has to equal 0, right? So if we pull out all these constants, what we're saying is that this has to equal negative E over rho integral of y dA. We know none of these terms can be 0, right? And by like, I think it's the fundamental theorem of algebra or something. Maybe I'm wrong. But anyway, integral of y dA has to be equal to 0. And if you remember the definition of the centroid that we gave, I think it was in the statics review, the centroid is actually just the integral of y dA over integral of dA, right? It's the weighted average of the points with respect to the area, which means that, like I said earlier, this point right here, this central axis, because remember, we were looking at y as the height off this central axis, has to occur at the centroid of the cross-section. And now the next thing we want to do is we want to go ahead and sum the moments around the z-axis. So you can see right here, if this is my x and this is my z is going to point out of the page. So basically we're looking at this axis right here, right? So I know that the sum of the moments and the z-axis has to equal 0. So on the slice right here, I'll just have a negative m. We'll go ahead and write that second. The other thing I'll have is I'll have it from these stresses, right? So I'm going to put a negative sign here, and then I'll just explain it real quick. So we're going to have the integral over our area. Now we'll have our sigma x dA. That'll give us our forces, but we're talking about the moment here, so we also need to multiply by y, which is the distance off that centroid or that neutral axis. Now the reason we have the negative sign here is because by sign convention, this right here is a positive moment, right? So positive moment, for that to happen, we need, when there's a positive y, we need a negative sigma x So we put the negative sign out here so that if we have a positive y and a negative sigma x, which means compression, then this whole term works out to be positive. Then we also need a minus m, because our m is going this way, right? That's a very kind of complicated way of saying it. Basically, because our z-axis points out of the page, this direction is positive, which means that our m here is negative, and if we want this term to have the right sign, then we need to put a negative out front. So now we can go ahead and plug in, if you remember from earlier, our epsilon times our e will equal our sigma, so we go ahead and we go down here, and we can pull this all out. We'll have it equal to e over rho, and then we'll have integral of over our area y squared dA. I pulled these out because they're constants. And now what we're going to do is we're going to define this whole integral right here as a quantity called I. It's off the z-axis, so we call it iz equals integral over area of y squared dA. This is called the area moment of inertia. Sometimes we'll just call it the moment of inertia, because technically we could have this like dm and we're integrating, we have to multiply by the density or something. But in this case, we're just going to look at the area, the geometry of it. So now what we can say is that if we add over this m, then our m has to equal all of this stuff right here. I should basically have a minus m right here if all of this is equal to 0. We add over the m, and we get this has to equal to e I z over our rho. Now remember, because we're trying to find our stress, that's really what we want here, right? Remember that we said sigma x equals negative e y over rho. And now what I can do is I can solve each of these for e over rho and set them equal to each other, right? So this implies that negative sigma x over y equals e over rho. And then this also implies that my m over I z equals e over rho. And now I can set them equal to each other. So I get that my negative sigma x over y equals m over I z. And solving, we get that the horizontal stress at some point on our beam is equal to negative the internal moment times the height off the neutral axis that we're looking at, divided by the moment of inertia around that axis. And this is a very important equation. You're going to be using this one all the time, basically for the rest of solid mechanics and wherever you use this in the future, like FEA or something. Now we can also have a shear stress when we have beams that are being acted on like this. So if you imagine, like if I just have some beam, right, and I go ahead and I bend this downward, maybe I fix this at one end and then put a force like this, it's going to want to bend downward, right? And so you can imagine, like, if it was made of a bunch of tiny fibers, like if instead of the beam I had like a fiber here, a bunch of fibers going along the length, and then I bend them downward, they're going to slide past one another, right? So you can imagine like this would bend down like this. That's not a great drawing. And then this one would maybe bend down and go a little bit further. And then this one would bend down and go a little bit further, right? And so that's the idea, is that in order to hold all these slices together when it's being like held together because it's composited, like it's glued or something, there's actually a shear stress in the horizontal direction that's called the transverse shear that's holding these together. And so to go ahead and derive that, we're going to look at a slice of our beam. So you can see right here, we basically got our distributed load. On the left, we've got our shear force. On the right is our shear plus, we're calling it delta V. And then we've also got our moments, which could be there, right? So we're assuming that V looks like this. These are our positive sign conventions. And what we're going to go ahead and do is actually we're just going to look at everything happening in the horizontal direction of some slice of this from the top, basically. So if we go ahead and we imagine, like, we take a slice. Do I have it right here? I do have it right here. Okay. So I have a slice from the top right here, right? And I'm just concerned in the horizontal direction because we're just going to do a sum of the forces in the x direction, right? So on this slice right here, theoretically, I'm going to have my moments applied, right, in the x direction. So that's going to cause a compressive stress. It's going to get higher as I go further up. And as we saw earlier, it's going to equal my over I. So if my moment on the left here is just m, it's going to be m times y, which would be the height of wherever we are right here. So like the y would be up to here or up to here, right? And the I is off the z-axis. So basically this is like a slice of the length, right? But if we rotated it, where this is my z-axis. So if I rotate it, so now like the z-axis is this way and the y-axis is this way, I would have like a cross section right here, and the moment of inertia off the z-axis, so basically in this direction, is the IZ we're looking at. And then over here we just have the same thing for m plus delta m, right? And then lastly on this segment, we're going to have some kind of force here acting from the rest of the beam because we're just analyzing this part in the x direction. So summing all the forces in the x direction, we know they're going to equal 0. We're going to have the integral over m over IZ, and then we'll have a y dA prime. I'm calling it A prime because this area is not going to be the same as the cross-sectional area of the whole beam. That'll be to the right. Then we'll have to subtract an integral of m plus delta m all over my I in the z direction, y, and then I'll have a dA prime. And then lastly, I'll have to add this FH. So if I go ahead and I cancel out basically this m over IZ y dA, because I also have a negative m over IZ y dA, this is going to give me 0 is equal to integral of what? Delta m over IZ across the A prime, dA prime plus FH. Or I can go ahead and add over this FH. So you know FH equals integral of my delta m over IZ dA prime all across the A prime. And now I'm going to go ahead and define the integral of, oh, I think I dropped a y somewhere, right? Because there should still be a y getting multiplied by this delta m up here. So there should still be a y. And across the area, because we're integrating across the area, neither my delta m or my IZ is going to change, so I can pull these out, right? So I get FH is equal to delta m over IZ, integral of y dA prime, and you've kind of seen what we're doing so far. We're going to go ahead and define this integral of y dA as Q, which is called the first moment of area, integral over some area. We'll just put a prime here so it's consistent, right? And then we can go ahead and write this as FH is equal to delta m Q over my IZ. And now, because we're not interested in just the shear force, which is what this is, right? Because it's parallel to this this area right here that we're looking at. We're interested in the shear stress. And we know the shear stress, we'll just call this like tau H is equal to my shear force, and maybe this is the average since we haven't taken a limit yet, divided by the area it acts across. Now the area it acts across is going to be this delta x times this thickness in the z direction, which we're going to call t. So if you imagine like my cross section down here, right, I'm going to have a t here, and I'm also going to have a delta x. So we can go ahead and divide this by delta x times t, which if we go ahead and plug this will give me delta m over delta x, and then I'm going to put these together because you're going to see what we're going to do here in a moment. We're going to have a q over IZT, then we're going to take the limit as delta x approaches 0, so this is just going to become my shear stress in section H is my dm over dx q over IZT. Now if you remember what we were doing with the shear moment diagrams, this dm dx is the same thing as my internal shear force as a function of x. So I can go ahead and write this as shear equals v q over it, and this, again, I'll just put a z here. T is going to be one of those things you're going to be using a lot. Definitely box this one up. Now you notice I dropped the h, and that's because the shear stress is going to be in all directions, right? So we had the shear right here, but if you imagine an element, we talked about this earlier when we were introducing stress, all of the shears have to be equal in magnitude, right? So if I have a shear stress like this, I'm going to have an equal shear stress acting here, acting here, and acting here. So if I solve for any one of them, then I know the whole state of shear in this element if it's in equilibrium. So real quick, I just want to talk about these quantities I, Q, and Y because they show up in these equations. We've talked about them, but it may not be clear, like from a computational perspective, what exactly we're going to do. So I guess we can just go ahead and start with Q. If you remember, Q is called the first moment of area. It's defined as the integral over our area of our Y. I think it's Y. They put a tilde here. dA. So basically the way you can think of this is we're summing up the y of kind of the centroid times dA. And it turns out that this is an integral, right? Because normally we would basically take this object and we'd break it into a bunch of tiny differential chunks, and then we would add up the y tilde off of our axis. Let's say this is my axis right here. So if you recall from earlier, we picked some arbitrary area off of basically the top of this, right? And then we went ahead and looked at what the shear stress would be of this area. So we're talking about y. Our y is still going to be, it's all the way down here, I forgot. Our y is still going to be basically off that centroid because that's where our axes are, right? Our y is still right here. But our a is just going to be from the edge to the point where we're examining the shear stress. So basically, if our centroid was like right here along, let's just say it's this axis right here, right? And then I want to know where the shear is at like this point right here. We're really just concerned with how high it is. So let's say I want to pick right here. Then my area would be all the way from the edge down to this point right here, right? And because in this case it's just a rectangle, I know it would be the center. So theoretically, if I'm given enough dimensions, I could actually find this. This would be my y tilde. And then my a would just be the area of this right here. And because I know that that's the centroid, I could actually just turn this into a sum. So this just would be the sum, which in this case wouldn't even be a sum because we would just have y tilde times the area of this single rectangle. But if it's broken up into chunks where you can just add it up like this, then you can just do, your y times your a for each of these areas. So if I have a more complicated thing, like let's say I have maybe like a material that's like a hollowed out square, right? So I have this. All right, my neutral axis is going to be right through here. And maybe I'm looking at it, let's say I'm looking at it on the neutral axis, right? So I'd have to consider all of this area right here. And you can kind of break it up however you want. Maybe I break it into like a rectangle right here and a rectangle right here and then one more right here. And then I can say, so I have a y bar right here, which would go to here. I'd have a y bar or a y tilde right here, and then I have one more y tilde right here, and then I'd multiply it by those areas. So if this is like area 1, area 2, area 3, and then this length right here is y tilde 3. I'm running out of room here. Y tilde 2, and then this right here is y tilde 1. Then I would just get that my q is equal to, right, y tilde 1 a1 plus y tilde 2 a2 plus y tilde 3 a3. And then if you're looking at something that's below the neutral axis, you're just going to go from that edge instead. So for example, if I was looking at this point right here, then my area would be right here, just like this, and then my y tilde would basically be to the centroid of it, point like right here. Now our y bar, which is the coordinate of the centroid, is kind of related. You can see we basically have the same term right up here, except it's not defined exactly the same way because, so for q, we had to have a y off the neutral axis, right? But for y bar, if it was on the neutral axis, then our y bar would always be 0, right? So we pick it with reference to some system, like let's say I have some object right here. This is like an I-beam, right? And let's say I pick my reference axis, they call this a datum sometimes, to be right here. Well, then what I would do is I could integrate these. So this could be an integral here and an integral here. If you have a very like weird object, but you have continuous functions that describe them, you can also do the discrete summation case, right? So what I could do is I could break this into 3 rectangles. So I would have a rectangle on the bottom right here, right? I could have one right here, and then I could also have one more right up here. And what I would do is I would label these. So whatever the area of this rectangle right here is, I could call it A1. All right, yellow, I guess we're going with yellow. This would be A2, and this would be A3. And then for the y, that would just be the height to the center of it. So this right here would be my, right, y bar 1. Up to here would be y. I keep getting my bars and tildes confused. The tilde is for the individual components. The bar means the position of the centroid. So this right here would be my y tilde 2, and then up all the way to here, I would have y tilde 3, and then I would have to divide by these. So in this case, I would have, right, y tilde 1, a1 plus y tilde 2, a2 plus y tilde 3, a3 over the sum of the areas because it's like a weighted average, just like this. And now if your thing isn't a rectangle, y tilde is just going to basically be the center or the centroid of that object. So it's a little bit weird. It's almost like recursively defined, where like you would need to find the centroid in order to find the centroid. But if you can break it into composite areas, so for example, let's say I have like a circle, right? And I kind of know the centroid is going to be the center of it, or even if it's something weird, but I can integrate and find the centroid. So like if I integrate this half circle, right, I can find a function for my y tilde if I break it into like differential rectangles and all that, right? Once I figure that out, I can use this as if it was a composite area. So like, for example, if I had a half circle and then a rectangle connected to it, I could do a weighted average of basically this being one of my centroids, this being the other centroid, and then I have the area of this this shape right here, I guess, and then this shape right here. So the last thing we have is I, which is equal to the integral of y tilde squared dA. And this one isn't quite as simple as the other ones we've seen because we have this y squared. We can't just break it into sums exactly like we've seen where you just look at like the center of a rectangle or something. So instead what you'd have to do is you have to break it into composite areas and compute the integral for some of these composite areas. Like for example, if you integrate for basically a rectangle right here from the centroid, so wherever your centroid is, off of this centroidal axis, right, where we have some height h and some width w, it turns out that the I is equal to 1/12 wh cubed. So we can use this in combination with composite areas, or you can evaluate this integral for like other shapes and combine them. Basically, the way this works is that normally we want it from some axis, not just the centroid, right? So like for example, if we're trying to compute IZ, then we need the moment of inertia off the z-axis, right? So if you imagine like we have some shape right here, right? Like let's just say we have a shape like this, and I know that this right here is my centroid, right? But then I want it from some, we'll just call these like the xy axes, right? So what I could do is I can call my new moment of inertia, let's just call it I prime. This would have to equal integral of, well, normally I would have my y tilde, which would be from the centroid, but I also need to take into account this distance x. So if I go ahead and call the distance between the x-axis and this axis right here, they call it d sub y, I would have to add my d sub y, then I would take all of that and I would square it, and I'd have my dA, and if I go ahead and I distribute this across, this would give me a y tilde squared plus 2 y tilde dy plus, and then we'll have a dy squared, all of this dA, and now I'll have three terms that are going to come out of this, right? The first one is going to be my y tilde squared dA, which is just equal to my original I at the center of mass. Now the second term right here, when I integrate y tilde dA and then I pull out these constants, we'll have a dy and a 2, and I can pull those out, right? When I'm just integrating y tilde dA, remember that y tilde is relative to the center of mass, which actually means that if we do this here, it's at the center of mass, which means it's just going to cancel out and go to 0. And then lastly, we have this term that's integral of dy squared dA, and since dy squared is a constant, we can pull it out, and this is just going to become a times dy squared. So this is our I prime right here. So basically, if we happen to know the I of the center of mass, like let's say they give you your w and your h, so you can get I center mass, that's 1/12 wh cubed, and then you can add to this the area of your shape times this y distance squared in order to get the moment of inertia from some other axis. And if you had multiple shapes, you would just add them together, right? So if I had like another square right here, I would just add my 1/12 wh cubed plus whatever this second dy is, we'll just call this like dy2 times this area, so my dy2 squared times my area. And you could do this again, the same for any kind of other shapes. Any kind of shape where you could find an equation that's going to tell you what your I at the center of mass is, which you get from evaluating this integral. So really, this integral is like the main like building block, and then we go ahead and we can take that and break it into things that are a bit easier to work out when we can break our shape into simpler composite shapes.